So our speaker today is Michael Bevis. He's from Ohio State University. He's a geodesist who has been using GPS receivers extensively around the world in the Amazon Delta region, the Amazon Basin, and the Antarctic, and he's also instituted an observing network with international collaboration around Greenland. It's been in effect now for a number of years and observes the seasonal and long-term trends in a variety of parameters, but he can then take those and deconvolve them to get a handle on the expansion and contraction of the Greenland ice sheet. And he's agreed to give us a presentation on the wonders of this array today. So, Michael, it's yours. Are you there, Mike, or are you muted?
My cell phone, or can I talk to the computer?
Whatever you're doing right now is working.
Yeah, we can hear you now, whatever you're doing. No.
Okay, so I'm plugging into my cell phone.
Okay,
so
thanks.
I'm told this is, like 20 minutes kind of talk, so I wanted to zero in on what I think is the most interesting thing we're studying right now, which is this amazing anomaly that occurred in Greenland in 2013. Some people are calling this the pause. I like to think of it as the melting season that did not happen. And what I want to do is talk about that in the context of what did happen fairly consistently in the preceding decade, which is almost steadily accelerating ice loss. So you had a decade of accelerating ice loss followed by this sudden cessation of seasonal melting. So GNet is a GPS network. It consists of something like 50 GPS stations. They're all built into solid bedrock surrounding the ice sheet so that they are really measuring what the lithosphere is doing in response to what's happening with the ice. And this is sort of like one of two direct mass sensing systems. So the first one, the most famous one, is GRACE, which measures mass change via gravity change. And what GPS does instead is it measures mass change by exploiting the fact that the Earth is inelastic. So when you put a mass on a spring, it's compressed. And if you take that mass off that spring, then that's released and it expands. So we know that the Earth is inelastic because the elastic waves, earthquake waves in it, we know roughly its elastic properties. So when you put ice on the Earth, there's an instantaneous elastic adjustment. It's compressed downwards. And when you release the weight of ice, the ground rebounds. And on the picture on the left, you can see the GNet, and these are sort of average lifetime velocities. It has to be interpreted with a certain degree of care because they have different lifetimes. Some stations were built in 2007, some in 2008, and some in 2009, so that those lifetimes correspond to different time spans, and so one needs to take that into account. If you look at the scale, the tallest one is about 30 millimeters per year. You can see the scale on the bottom right-hand side. If you compare this to sort of the typical vertical velocities around the world, so if you do that, if you look at just global solutions for hundreds of thousands of stations, typically GPS stations move up and down by 2 or 3 millimeters per year. Whereas here, the typical vertical motion is 15, 20 more millimeters per year. So these extraordinary vertical movements represent Earth's response to the loss of weight holding down this elastic material. And if you look at this plot, what you can see is that the biggest velocities tend to be in the southeast and the northwest parts of Greenland. And that's not entirely surprising, given that Grace was already showing, as you can see in John Lahr's image from early 2011, I think this image was made, which shows the mass change over a 4-year period, 2003 to 2007, and then the mass change over a 7-year period. And you can see that in the beginning it was largely the southeast, but then later on you also see significant loss in the northwest. And if you look at that John Lahr's plot, it's sort of immediately obvious that there's been an acceleration in mass loss, at least in the northwest. All right, and so we shouldn't only expect to see velocities, we should expect to see accelerations in the GPS uplift rates, and we do. In fact, these accelerations can be surprisingly large. So the station KAGA, which is sort of over on the left, the west coast, in the middle of Greenland, it's the station that's closest to Jakobshavn, and it accelerated from during its lifetime from about 8 or 9 millimeters a year to something like 32 millimeters a year of uplift. The second biggest outlet glacier, of course, is Kangaroo, and we have a station KUAQ, which is next to that outlet glacier, and that's sort of, also one of the very fastest uplifting stations in Greenland. And early on, it was the fastest, but in this case, it's decelerating. So it went from 30 millimeters per year nearly down to something like 25 during the course of our observations. So this is another reason why it's not that, it's sort of dangerous to look at velocities, because not only are the stations got different lifetimes, but velocities are not constant over a large fraction of GNET stations. Acceleration is at least half of the stations have detectable accelerations. So it's sort of following the dynamics of mass loss. Of course, you can't really just interrogate what's going on with the ice and climate change only using Grace and GPS. You also have to use repeat altimetry and direct measurements of change in surface height and the velocity of the ice flow. I'm going to sort of de-emphasize those because there's really not enough time to talk about 4 different measurement systems and how they should be integrated. But clearly the long-term goal is to make combined solutions from Grace and GPS, which are direct mass sensors, and other remote sensing systems that provide better spatial resolution and better coverage. The different techniques have got their different strengths and disadvantages. GPS has got excellent temporal resolution, and it's very sensitive to what's happening at the edge of the ice sheet. Grace has got poorer temporal resolution, and it's very smooth in space, and it's sensitive to what's happening to the interior as well as the edges. Repeat altimetry has got superb spatial resolution and very good coverage, but there's difficulties relating change in the height of the surface to the change in the mass, because the density of the near surface is variable in both space and time, and that's a significant complication, and so on. Here's a picture that I just generated fairly recently for the AGU, showing Grace again. This is actually using the Princeton solution, which is uses Schleppian basis functions to confine the solution to the general area of Greenland, and so it sort of suppresses a lot of stuff that's happening outside of Greenland, like changes in ocean currents. And this shows you sort of 3 time steps rather than 2, like the previous John Lahr picture. So you're seeing the first, the reference point now is sort of 2003.12. So I start at that and say, okay, let's look at mass changes since then. So the first one shows you sort of 3 years, and the second plot in the middle shows you sort of 6+ years, and then the last one shows you about a little bit more than 10 years of cumulative mass change. What makes this a bit different from Januar's is I've removed the average seasonal cycle, so that this is the sort of the progressive trend in mass change without the seasonal cycle being there to alias into what you're looking at. Now, I'll talk a little bit later about how we actually did this decycling or seasonal adjustment. But right now, I'd like to point out that you sort of see, you saw early loss concentrated in the southeast, but even after 6 years, you were seeing the loss in the southeast and the northwest. And one thing that people often miss is that in the high interior, especially to the north, there's actually a mass gain coming out of the gray solutions. And in the early years, you see mass gain also in the southwest, so centered around Nuuk and Kangaroo airfield. You see that's got that blue color. So this is a place that sort of actually has tended to reverse what's going on. It was gaining mass, and then later on it turns out to be losing mass. You also see in the northeast corner that there's eventually you see there's actually significant loss developing in the northeast as well as the south, the southeast, and the northwest. I just want to, I'm sure nearly all of you are experts, but maybe one or two of you are not. So I just wanted to point out that the Kangaroo glacier I'm talking about is the one that's labeled as number 1 in this map showing velocities, and it's the number 1 in the famous list published by Enderlin et al. GRL. Number 2 is Kangaroo. The interesting thing is if you look at that group in the southeast, this 6 through 7, you see that collectively that group would be number 1 if you added up all of the contributions. So it's pretty clear why 2 through 7 is an area of major rebound. And when you look at all these little red outlet glaciers, you can also sort of see why 1 through 10 is important. These are places where you have marine terminating glaciers, and part of the solution is part of what we're recording with GPS is dynamic loss, and then part is surface mass balance. So if I went back to like where we were a few years ago, this plot on the top shows the Princeton gray solution integrated over all of Greenland. And you can see that what I'm doing is I'm modeling this in the same way that I do the GPS. I'm modeling as an annual cycle superimposed on a quadratic trend. And the reason why I use quadratic is you really can't have a linear trend. The trend is clearly curved. And so that dashed line represents the curve. And I use a 4-term Fourier series, a sine and cosine with a period of 1 year and a sine and cosine with a period of 6 months to capture the seasonal cycle that's superimposed on that trend. And that sort of shows you that there's been a fairly strong increase in velocity. And we could actually, since you can take a quadratic and you can do the first derivative and get rates, those 3 color plots beneath the graph represent the mass rate solution coming out of grace. And then you can do the second derivative, which is acceleration, and the top right plot shows mass acceleration. And that's sort of interesting because you get a somewhat different impression when you look at rate, and you get a somewhat different impression when you look at acceleration. So when you look at rate, you do see, wow, there's that initial opposite sign in the southeast corner at the beginning. The mass was gaining rather than losing. And then in the middle picture, you sort of see, the southeast and the northwest. But by the time you see the third mass rate. You notice it's the whole West Coast that's losing mass, and part of the Southeast is backed off. It's not losing it like it was. When you look at the acceleration plot in the top right-hand corner, what you notice is, wow, the maximum acceleration is well to the south, exactly south. So most of the signal has to be surface mass balance and not glacier in terms of the acceleration. The station Kellyville, is fairly close to